In this lecture we will look at the concepts of conditional probabilities and the multiplication rule. In essence, we've seen both these concepts before, but we have not put those names to them. For instance, in the previous lecture when we had 10 pieces of candy, all the same size, except that 7 were cherry and the rest 3 were lemon. We talked about the probabilities of getting sequential events. For instance, we could talk about the probability of getting a cherry on the first draw selection and a cherry on the second selection. Right, and from what we've seen already in the previous lecture, the probability of getting a cherry on the first, well, there are 7 cherries available to be selected out of 10 possible choices, so there's 7/10, or 70% probability of making that first selection. And then the probability of getting a cherry on the second, well, we multiply those probabilities. Well, we have 9 left to select from, of which 6 are cherry. Okay, and that's the probability. But this involves both parts of what we are going to talk about in this lecture, that is the conditional probabilities and the multiplication rule. Alright, so let's put some structure to this. Alright, why isn't the second probability, 6/9, equal to the first probability, the 7/10? Well, we sort of know that story. That is, once we've taken a cherry on the first draw, the probabilities change. Alright, or another way of looking at that is that the 6/9 is the probability of selecting the cherry on the second selection given that, I'm using the typical words here, the cherry was selected on the first. Time round, okay? And you must of course understand that the probability of selecting a cherry on the second depends greatly on what flavor piece of candy was selected on the first. If lemon was selected on the first choice, then the probability of selecting a cherry on the second would be 7/9 and not 6/9. All right. So anyway, this is a conditional probability. This 6/9. It's conditioned on the fact that a cherry was selected on the first. Okay, that is different probability if we had a different condition. As we said, what would change would be different if a lemon was selected on the first draw. All right, so the condition changes the probability. All right, to write it down more like we would write it in the notation of probability theory, we would call this the probability of a cherry. I'm going to abbreviate this on the second drawer, straight up and down line, which stands for given that, cherry was selected on the second drawer, and that's our 6/9. Okay, so this is a conditional probability. So this straight up and down line is equivalent to the words given that. There are other ways of specifying a condition other than the words given that, and that's where students have problems, to be quite honest. Okay, so but try to see if you have words that you can replace with words given that. For instance, quite often the word if can be replaced with given that. Okay, and that would signify a condition. All right, but going back to our example, all right, so we had the probability of cherry on the first and cherry on the second would be written as the probability of a cherry on the first times the probability of a cherry on the second, given that we had a cherry on the first. Okay, and that is essentially all we're talking about in this lecture. All right, we have conditional probability, all right, this second element here, and this whole equation is called the multiplication rule. So, in general, the multiplication rule all right, for two general events A and B. So the probability of event A and event B occurring is written as probability of event A times the probability of event B, conditioned on given that event A has occurred. Okay, and so that's our multiplication rule. Okay? And remember that. While we're at the multiplication rule, just like when we talked about the addition rule, we had the concept of mutually exclusive. With the multiplication rule, we have the concept of independence. So we can say that two events, say A and B, are independent or not related if the probability of A and B is equal to the probability of A times the probability of B. In other words, no conditional probability. All right, an example of this is a coin toss, or generically sampling, selection, whatever you want to call that, with replacement. All right, so this equation that I have here is only true if we have two events which are independent. Okay, if we have events that are dependent, like in sampling without replacement, cherries, pieces of candy in a jar and with lemon pieces, all right, then we have to use the multiplication rule as above. All right, or another way of saying this is that if two events A and B are independent, the probability of B is also equal to the probability of B given A. All right, the probability of a head on the second toss is equal to the probability of a head on the second toss given a tail on the first toss. It doesn't matter, all right? Okay, so the condition is meaningless. So therefore, we can say we can drop the condition. All right. But to be quite clear about it, if A and B are dependent, not independent, some students like to say, then the probability of A and B is not equal to the probability of A times probability of B. Okay, that is probability of B without the condition. All right, and that's quite often how we prove that A and B are dependent. All right, we get the probability of A, the probability of B, multiply the two, and see if they equal the probability of A and B, and if they're not, hey, they're dependent. All right, and we'll see examples of that later. All right, let's note the following, that the order of the events A and B is not important. In terms of just writing them down. So the probability of A and B is equal to the probability of B and A. Okay? Sometimes it makes more sense to write the events in particular order, but in terms of symbols, it doesn't matter. Okay? But we might notice that although the probability of A and B is equal to the probability of A times the probability of B given A, if we just switch the formulas, sorry, not the formulas, but the events around, call A B and B A, all right, so the probability of B and A is then the probability of B times the probability of A given B. And I can just do that with any symbols I want, but from the above, we have these two events are equal. So in other words, these are equal too, all right? So the probability of A times the probability of B given A is equal to, right? Not that both sides are equivalent, but they're equal. Probability of B times the probability of A given B, and sometimes that formula is useful when we're doing problems. Okay.